طيب, today inshallah we are going to continue in the determinants. We have Cramer's rule, how to solve system of equations, and the system here we are going to talk about a system where the number of equations equal to the number of unknowns. So the matrix A, the coefficient matrix, is a square matrix. We can solve this using determinants, using what is called the Cramer rule. And then we are going to find the inverse of the matrix, what is called the inverse. If you have AX equal B, I'm going to find what is called the inverse of the matrix using what is called the adjugate method and using Gauss-Jordan method. And then we are going to define what is called the elementary matrices and find its relation to the row operation of Gauss. So let's first start with Cramer's rule, how to solve a system where A is a square matrix. So we'll have here in this lecture, we are going to talk about a matrix dimension n by n in general. Okay? So assume that I have a system AX equal B where A is 3 by 3. And let's define the identity matrix. You know, I3 equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. So let me call these columns as vectors E1, E2, and E3. Okay, so this is the identity I3. Okay, and I'm going to solve this system AX equal to B. Okay, let's see what Cramer did to solve this system. Let's multiply the matrix A by the identity matrix, for example, but I'm going to replace the second column in the identity with X, which is unknown for me now. So we're going to solve a system AX equal B, where A is 3 by 3, X is 3 by 1, B 3 by 1, and you know A and B, and you don't know X. Okay? Let's see what happens if you multiply the matrix A by this matrix containing E1, which is this guy, then X, instead of this guy, I'll put X, and then E3, the third column of the identity. When you multiply matrix multiplication here, you will get a matrix 3 by 3 and its first column. Let's see what we get in the first column. If you multiply A by E1. Okay, let's write A as columns. So I'm going to write the matrix A as A1, A2, A3. And I'm going to multiply this matrix by the vector E1, which is 1, 0, 0. So what do we get? A1, مش كده? Actually using linear combination. We do linear combination between these columns using these weights. So we'll get directly A1. What about AX? What is AX? I'm solving this problem. So AX equal B. What about AE3? It will be something similar to this guy, but we'll have 1 in the last row. So we'll get directly A3. Right? So this multiplication would produce A1, then B, then A3. Right? Let's take the determinant for both sides. So we'll have here determinant of product of two matrices. So the determinant of the product equal to the product of the determinants. So on the left hand side, actually I'll get determinant of A times the determinant of this matrix containing E1 x E3. And this guy equal to the determinant of E1 B A3. Okay? I'll take the determinant for both guys. Which one? This guy? Now on A times E1. A times E1. And the result I'll put it in the first column. These are E's from the identity. And I replace the second column of the identity with X and define this matrix. So this matrix contains the columns of the identity except the second column. I replaced it with X. And according to the multiplication, you will get here A1 and here A3 and here AX equal B. Then I'll take the determinant for both sides. Okay, so we'll get this equation. Let's find the determinant of this guy. Okay. What is the determinant of E1 x E3? E1 is 1, 0, 0. X would be a vector of three variables of unknowns, x1, x2, x3. And E3 is 0, 0, 1. So what is the value of this determinant?
X2.
X2, right? You can expand using the first column, so we'll get X2 direct. So this guy is X2. And this guy is the determinant of A, the coefficient matrix. And this guy is the determinant of A, but I'm replacing the second column of A with the right hand side of the equation, okay, which is B. So we can conclude that X2 equal, this guy now is X2. So X2 equal to this number over this number. These are scalars, right? So X2 equals determinant of A1 B A3 over determinant of A. This is actually the proof of Cramer rule. If you want to get X2, then replace the second column of the matrix A with the right hand side of the equation. So you are solving X equal B. So replace the second column of A by the right hand side. You'll get another matrix here, get the determinant of this matrix and divide it by the determinant of A to get X2 directly. If I want to get X1, what do you expect to the formula for X1? X1 is a variable, is a scalar equal to determinant of B A2 A3 over determinant of A, and so on. So according to the position of your variable, you replace the column of A with the corresponding vector B. So we can conclude that in general we will have this formula. Xj is the determinant of A, but replace the jth column in A with B over determinant of A. So this is a closed form for any variable directly. Let's see an example, a quick example. If I have this small system, Ax equal B, and I want to find x1 and x2 using Cramer's rule. So first I'll find the determinant of A, which is this guy, the determinant of A, which is 12 minus 10, which is 2. So this is the first thing to find, the determinant of A. And then I'm going to find what is called A1 of B and A2 of B. First, I'm going to replace the first column of A with B and find the determinant of this new matrix. So this is called A1 of B. Replace the first column of A with the right-hand side and find this determinant. Then find A2 of B, replace the second column of A with B. So replace this guy with this B and find this determinant. So to find x1 equal to determinant of A1 of B over determinant of A, which is 40 over 2, which is 20, and x2 determinant of A2 of B over determinant of A, which is 27. So you have here a closed form for each variable. So do you find any disadvantage of this method, Kramers? Is it good to use this for high dimension, for example? You'll get a problem. You'll have here to find determinants in high dimension. So it will take time if you expand the determinant using cofactor, for example. The better way is to use reduction, as we said in the previous lecture, to find the determinant. So if you are going to do the reduction, then solve the system using reduction. Okay? So this is actually, we use it for small system, 2 by 2, 3 by 3. Okay? But for large system, it's better to use Gauss elimination with back substitution. Plus, this method can be used only in the case of A must be square and determinant of A not equal to 0, and you will get actually a unique solution in this case. So it's used only in the case for unique solution only. Okay? طيب. Let's now find a formula for the inverse of A. The inverse of the matrix A, the square matrix A, is defined such that the product with A from left or right, you will get the identity أو المحايد بتاعنا اللي هو ال I. Okay? We need a method to find this guy. How to find this guy such that you multiply it by A, you will get I. Okay? Let's see it for a simple example. If you have A 3 by 3, okay, this is an illustrative example. We'll show you that if you have A and B, and if you multiply these matrices together, AB or BA, you will get the identity. So I'll give you one of them, for example, this guy, and I want a method to get the other guy. Okay? So we say that B is the inverse of A, or A is the inverse of B. Okay. So assume that A is 3 by 3 matrix. Okay. I want to find the inverse of A. I write it in columns X, Y, and Z, such that when you multiply A by inverse of A, you will get the identity. And I write the identity as columns E1, E2, E3 as before. Okay? Now I'm going to find a way to find these guys. What is X? The first column of the inverse, Y, and Z. So let's write it this way. A times the inverse of A would be I3. So A times the inverse, which is X, Y, Z, equal the columns of the identity. From this, we can say that AX equal E1, AY equal E2, AZ equal E3. Let's take one of them. AY, for example. AY must be equal to E2, which is 0, 1, 0. Okay? Let's find the first variable in the column y. Y, as you know, is a column. So it contains y1, y2, y3. Let's find the first variable in the vector y using Cramer's rule. How to get the first variable here using Cramer's rule? So we say that y1 equal using Cramer determinant over determinant. A1 of E2, which is the right hand side, over determinant of A. Right? Don't forget y is y1, 2, 3. And I'm getting the first one. The first one, so replace the first column in A with the right hand side and take the determinant of this guy divided by determinant of A. Let's see this guy. What is this guy? I'm going to replace the first column by E2. What is E2?
0, 1, 0.
0, 1, 0. And what is the second column? Be the second column of A, which is A 1, 2, A 2, 2, A 3, 2. And the third column of A, which is A1, 3, A2, 3, A3, 3. Right? Let's expand this guy along the first column. So what do we get? We're going to cover this row, cover this column. It would be this minor determinant with positive or negative sign?
Negative sign.
Negative sign, right? Negative determinant of A12, A13, A32, A33. If you look at this guy, we call this guy the cofactor, which contains the minor determinant with its sign. We call it the cofactor. The cofactor of which element? Of this element in the matrix A, which is A21. So this is C21. So we ended up with Y1 equal to C21 divided by determinant of A. What is the location of Y1 in the inverse of A? Y1 was the first variable in Y, which is the entry at the first row and the second column. So we write it this way. Y1 is 1 and 2 entry in the inverse of A. And we ended up with this guy, which is the cofactor C21 over determinant of A. So this is how to get entry at the position 1 and 2 in the inverse, the C21 over determinant of A. So can you generalize this if you want to find entry I and J in inverse of A? It would be cofactor Ji, not Ij. Cofactor Ji over determinant of A. So now I can get all the entries of the inverse. So each entry can be found using this formula. So let's write it in the matrix form to write the inverse. Let's see how it looks like. We write it this way. Look at this guy. So we'll have C11, C12, C13, and so on. But as you see here, there is reversing the order of I and J. So simply write here the usual cofactors, C1, 2, and so on, and then do the transpose to get this form. يبقى الانتري اللي هنا هتجيبه ازاي؟ هو C21 اللي احنا قلنا عليه. C21 هتيجي من الترانسبوز بقى. انت اكتب عادي خالص الكوفاكتورز، شيل كل انتري في الماتريكس A وريبليس ات وذ اتس كوفاكتور، كفر الرو والكولوم واكتب الماينور والساين بتاعته. بكده هتكتب الكوفاكتور انتري لكل انتري عندك في الماتريكس بتاعتك، وكلهم divided by determinant of A. عشان كده انا خدته common من الماتريكس كلها outside. دي هنسميها الكوفاكتور ماتريكس، او ساعات بيسموها الادجيت اوف A، والميثود بيسموها الادجيت or classical adjoint method. Let's see an example to see how to apply it. But as you see here, if I have determinant of A equal to 0, then you can find an inverse for the matrix. So we say that the matrix in this case is not invertible or has no inverse or singular. They are the same meaning. Okay? So let's apply it for this matrix, for example, to find the inverse. I'm going to use this rule. The inverse of A equals the cofactor matrix transpose divided by determinant of A. Let's apply it for this example. What is the determinant of A? 2 مش كده؟ Determinant of A equal 2. So the inverse of the matrix A is 1 over 2. I'm going to write here the cofactor matrix and then transpose it. What is the cofactor? Replace each entry by the corresponding cofactor. Cover the row and column of each entry and then write down the remaining minor determinant and apply the sign rule. So here I'm going to write 4, positive or negative 4? Positive. Don't forget the rule of sign. It would start with positive, then negative, negative, positive. Okay? And then for this entry, cover the row and column. So I'm going to write 1 with positive or negative sign, negative. And for this guy, cover negative 6. For this guy, positive 2, positive 2. The final step is to do the transpose, to change the rows and columns. You will get 4, negative 1 as column, and then negative 6 and 2 as column. Okay? If you look at this guy and the original matrix, you can conclude what we did in a simple way. What happened actually here? The main diagonal, we actually interchanged the entries, interchanged the entries of the main diagonal, and it changed the sign of the off diagonal. This is called the off diagonal, and this is the main diagonal. Okay? Okay. Here I multiplied half by each entry. So you can conclude that if you have a matrix like this in general, so its inverse would be 1 over the determinant. Don't forget this guy, please. Don't forget the determinant. And then interchange the main diagonal entries and change the sign of the off diagonal entries. Okay? So this is very simple for 2 by 2 matrix. You don't have to calculate anything except the determinant. You just calculate this guy. Okay, let's look at a higher dimension matrix. You have 3 by 3, what happens? Okay, assume that I want to find the inverse of this guy. The first thing is to find the determinant and then write 1 over the determinant and then multiply it by the cofactor matrix. So you can find the determinant using, for example, the cofactor expansion using the first row, whatever. So it would be 1 over the determinant multiplied by a cofactor matrix transpose. So what I'm going to write in the first entry cover the row and column. So it would be this minor determinant, positive. Cover row and column and write the minor determinant, it would be positive. The next one, cover the row and column, write the minor determinant, and here we'll have negative sign. Then the third entry, and move to the second row, repeat negative here, positive, negative, positive, negative, positive, and so on, blah, 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 blah. When you solve, you can directly find the value for these guys. This is for illustration. I actually wrote the sub-determinants here. And then find the values for these guys. And then find the transpose and multiply by 1/8. Then you'll get your inverse. Is it difficult? It's straightforward, but don't forget the determinant. Don't forget the signs. Don't forget the transpose. Okay? How to check? Multiply it by the original matrix and you'll get the identity. What is the disadvantage of this method? You can't apply it for high dimension again because you are going to find large determinants here. Can we find a way using reduction? You know that the reduction is the magic word in these chapters to find everything using reduction. Can you find a way using reduction to find the inverse instead of the adjugate method? Let's remember Gauss-Jordan. If you remember Gauss-Jordan method, let's apply it for the square system here. If you have a square, ax equal b. What we did in Gauss-Jordan, we write a augmented with b. And then do the reduction until you find if a is 3 by 3, for example. So you'll end up with pivot, and the pivots are ones. You get 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? And actually what we get here, x1, 2, 3, right? When you solve x equal b, these are the solution. x1, 2, 3. And this guy is actually the identity matrix. And this guy actually is the solution vector, right? So if you want to solve ax equal b using Gauss-Jordan, I start with a augmented with b, do the reduction until you reach I and the solution vector x. So can we benefit from this to get the inverse of the matrix? Blah, blah, blah. Can you benefit from this to get the inverse of the matrix? Again, let's write the identity in columns, E1, 2, 3. And then assume this guy is the inverse, x, y, z. So you can say that ax equal to E1, ay equal E2, az equal E3. So actually I'm going to solve this equation. Ax equal E1, ay equal E2, az equal E3. What are the unknowns in these equations? You know A, and you know the columns of the identities. And the unknowns are x, y, and z. So we'll get back to this system. Ax equal b, and you know A and b, and x is unknown. So how to get this guy, for example? I write A augmented with E1. Okay? And if you reach here I, then you'll get here x. What if I write in the right hand side E2? If you write here E2 instead of E1, so what do we get after reduction?
Y.
We will get y. If you write E3, after reduction you will get z. So instead of solving this problem 3 times, 1 for each guy, you just write A augmented with the identity matrix and then do the reduction here until A reaches I. Then the right hand side here would be the inverse of A. So you can summarize that. You write simply A augmented with I. Do row operation. This guy reaches I. This guy reaches the inverse of A. So we find a way to get the inverse using reduction. So let's see an example. Blah, 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 blah. I give you this matrix and I want to find the inverse. So I start with this. A augmented with I of the same dimension, and apply Gauss-Jordan and use this as your whole row. Take, for example, this guy as a pivot, multiply it by -1, all the entries, and sum up with the second row. Okay? So this guy, the pivot, do this row operation to eliminate these guys. So we'll get something like this, and then move to the second row. You can take this guy as a pivot. Okay, and do the elimination to eliminate these guys. So it's a little bit long, but it's much faster than the adjugate method. Okay, and finally we'll take this guy as our pivot, do the elimination here. So reach it here I, so this guy must be the inverse of A. Okay? Straightforward? Okay. What if I can't get here all my pivots? تبقى not invertible matrix, okay? It has no inverse. So for us, you can first calculate the determinant to check if the determinant exists, then apply the reduction for a small system. Okay? Okay, so we applied the adjugate method and Gauss-Jordan to find the inverse of the matrix. Let's define what is called the elementary matrices and see how these matrices are related to the row operations. Let's see the definition for the elementary matrix. So the elementary matrix is a square matrix defined as a matrix that is obtained from the identity matrix by a single row operation. So I'll take the identity and apply one of the 3 operations that Gauss used to get what is called the elementary matrix. Let's see example. This is example for a 4x4 matrix, which is obtained from I4 using single row operation. What is the operation? The change of the first 2 rows. مش كده؟ يبقى احنا عملنا بس interchange the first 2 rows single operation. Don't forget single operation on the identity. So I am going to call this guy as an elementary matrix, which is obtained from this interchange in I4. What is the determinant of this matrix? -1. مش كده؟ Because you did actually row interchange, and we said if you do single row interchange, you will change the sign of the determinant. The determinant of I is 1, so here the determinant is -1. What about the inverse? Can you find the inverse of this matrix? What is the inverse of this matrix? مم. طب let's find it using جاوس جوردن. جاوس جوردن كنا هنعمل ايه؟ I will augment this matrix with the identity. Right? And then I'll apply row operation until this guy reaches I. How to get I from this guy?
Change
To change the first two rows. Right? 0, 1, 0, 0, 0. 0, 1, 0, 0. 0, 1. طلعت ايه؟ دي ال I. دي اصلا E1 augmented with I. After reduction, this is I. This is the inverse of E1, which is E1 itself. So actually we interchange the first two rows in I to get E1, interchange them back to get I again, right? So the inverse is itself. Okay. Let's see what happens if you take this matrix and left multiply it with another matrix. Something like this. What would happen? I'll take this guy, multiply it with general matrix A.
الادجيسنت element في الماتريكس الثانيه هي اللي هتطلع.
multiply it كده. لا فين النيجاتيف؟ مفيش نيجاتيف ساينز عندي. لا multiply بالراحة بس. multiply كده حتى row by column. The first entry is هيبقى A21 واللي بعده A22. So you're writing actually the second row. If you multiply the second row here, you will get A11 and then A12. So you're going to write the first row. You'll get these guys. So what happened actually? Started changing the first two rows of the matrix A. Okay, so actually this matrix, this elementary matrix, comes from interchanging these guys in the identity. And when you multiply it with another matrix from left, it will do the same job on the matrix. Interchange the first rows of the matrix. لا أنا هوصل لحاجة معاك دلوقتي. إن أنا عايز أقول الإيكويفالنس ده إن الرو أوبريشن دي اللي أنا عملتها اللي هي interchanging of rows equivalent إن أنا عملت left multiplication by this elementary matrix. So row operation actually is a matrix multiplication. Elementary matrix left multiplied by your matrix والelementary دي فيها الأوبريشن اللي أنت عملتها. هجنرالايز الكلام ده. Let's see what happens to the determinant of the product. What is the determinant of this guy? Negative the determinant of A مش كده؟ والنيجاتيف دي actually هي النيجاتيف 1 اللي هي determinant of the elementary matrix. So you can write it this way. Determinant of E1A equal determinant of E1 times determinant of A. Actually we said this as a property without proof. This is actually the beginning of its proof using the elementary matrices. So we ended up with this guy. This guy equal to this one. Let's do another row operation on the identity. I'll take also I4 and what I did here is scaling of the first row by half. مش كده؟ دي a single row operation applied on the identity. So this is the operation on I4. What is the determinant of this matrix? determinant كام؟ half مش كده؟ دي diagonal multiply diagonal entries direct. what is the inverse of this matrix? Do something like I did here. Put I to the right and then apply row reduction until this guy reaches I, then you'll get the inverse.
الدايجونال بتاع الانفرس هيبقى 2 1 1 1.
Instead of half, it will be 1 or 2.
فانا هسكيل الفيرست رو في
If you multiply these guys, you will get the identity, right? So instead of half, you write it 2 here to get the inverse. So what happens if you do left multiplication with another matrix?
scaling the first.
Again, scaling the first row of A with this half. So this is actually the operation to get this guy from the identity, and when you do left multiplication with the matrix, it will do the same effect. So if you do row scaling, when you apply row operation in Gauss, you can again say that this is equivalent to multiplying your matrix with an elementary matrix containing the scaling factor. Okay? Here, what about the determinant of E2A? This guy. The determinant of this guy is half from the properties of the determinant, half determinant of A. And half is determinant of E2. So we can write it as determinant of E2 times determinant of A. What is the third row operation? احنا قلنا الايه الانترتشينج وقلنا السكيلينج اللي هي الريبليسمنت مش كده؟ الريبليسمنت فاكرينها؟ دي كده ايه اللي حصل؟ بص للاي 4 وشوف ايه اللي حصل to get this one. We replace the second row with the sum of itself with double the first row مش كده؟ يبقى دي الاوبريشن بتاعتها. R2 replaced with the sum of itself with double R1. What about its determinant? What is the value of this determinant? 1 because it is
row operation does not change the value.
احنا قلنا row replacement دي would not change the value of the determinant او ممكن توصل انها triangular matrix فيبقى product of diagonal entries. What is the inverse of this guy? What do you expect the inverse of this guy? نفسها? Instead of 2 it will be negative 2. مالها زي ما عملت كده حط الاي واعمل ريدكشن عشان تجيب ده 0 هتملتبلاي ده باي نيجاتيف 2 وتقاد مش كده؟ طب what happens if you left to multiply it with another matrix؟
The same row operation applied with the
بالظبط هتلاقي طلعت لك كده هتعمل رو ريبليسمنت برضه للسكند رو. طب و ended up with ايه بقى؟ ان كل الرو operations are equivalent ان انت بتعمل ايه؟ left multiplication للماتريكس by elementary matrices. طب نبص على الاكزامبل ده بسرعه كده simple example. عايزين نفايند الelementary matrix that produces B from A ونstate الرو operation وندescribe how it affects the determinant. كده احنا عملنا ايه؟ actually عملنا رو operation. انا بقول لك شوف لي ايه الelementary matrix that produces B from A. يعني ال A دي عملنا عليها رو operation اللي هي equivalent ان انا multiplied by elementary matrix
وانا ممكن اشوف الاوبريشن اللي انا عملتها
عشان اجيب ال B. شوف الاوبريشن
اللي انا عملتها في وابلاي على الايدنتيتي
بالظبط. exactly. ايه الاوبريشن بقى؟ يس انت بتقول الانسر بتاعت الاي على طول. طب الرو اوبريشن ايه؟ تعرف تقول لي الرو اوبريشن؟ اوكي ايه الرو اوبريشن اللي حصلت؟
R2 minus KR1.
R2 minus KR1 replacing R2 صح كده؟ apply this guy on the identity identity اللي هي 1001 apply عليها الاوبريشن يبقى replace R2 multiply دي by negative K وadd يبقى هنا اكتب ايه؟ صح كده؟ يبقى دي المفروض multiplied by A, B, C, D you'll get this B checked يعني بقى تعملها check يبقى انا جبت لك الاليمنتري ماتريكس اهي وجبت لك الرو اوبريشن والديترمينانت الريليشن between the two determinants the same مش كده عشان قلنا دي row replacement would not change the value of the determinant. طب ايه معنى السؤال ده؟ كان حد يقول لنا ايه كان انت عملت الاول ايه؟ عملت على الاي اوبريشن فجبت ماتريكس جديده اللي هي قلنا ايكوفالنت ان انت multiplied from left by elementary matrix. فانا عملت ايه؟ reduction another reduction which is equivalent multiplied by another elementary another reduction until you reach I. What happens if you take a square matrix and do the reduction until you reach I? According to Gauss-Jordan you use this to get the inverse. هو بيقول لك بقى write the inverse in terms of the elementary matrices. حد يعرف يكتب الانفرس in terms of elementary matrices؟ ده بكتبها لك هنا تاني. هو كان معايا ايه؟ عملنا رو اوبريشن الاول، عملنا another row operation، عملنا another row operation، واندت اب ان لقينا دي هي الايدنتيتي. يبقى what is the inverse of A؟ هو ده. Because you multiplied by A you get I. So this is another way to write the inverse of A using the product of elementary matrices. So inverse of A equal E3, E2, E1. Okay? I'm going to use the elementary matrices in section 2.7, I believe, in finding what is called LU factorization. So it has another application later on. So let's complete this theorem. What is the inverse of the inverse? Is it obvious? What is the inverse of the product? Is it inverse of A times inverse of B or inverse of B times inverse of A? Let's see how to write the proofs for these guys. We write AB times another matrix, you will get the identity. So this guy is the inverse of this guy, right? And then try to simplify to get this C. So I can left multiply by the inverse of this guy to get inverse of A, B, C equal inverse of AI. Inverse of AI is inverse of A. Inverse of A times A is identity multiplied by another matrix, you will get the matrix. Left multiply with inverse of B, so we'll get so C equal to, so in reversed order, okay, like transpose if you remember. So yes, so inverse of AB is inverse of B times inverse of A. And if you have ABC, find the inverse of ABC would be right in reversed order. Inverse of C times inverse of B times inverse of A. What about this guy? The inverse of A transpose. You can do something like what I did here, and you'll find out that this is the transpose of the inverse of A. So you can switch these guys. What is the inverse of scalar multiple of A? 2A مثلا. I have 2A. What is the inverse of this guy? What is the inverse of this guy? What should I write here? Half inverse of A. If you multiply these guys, you'll get the identity direct. So the inverse of this guy is half inverse of A. So actually, as if you take the inverse for each one, and this is a scalar, so its inverse is 1 over K. But if you have A power n, the inverse of A power n, A square, for example, I want the inverse of A square. I can get it from this one.
inverse of
We said that inverse of AB is B inverse A inverse. What about if you have A square? The inverse of A times the inverse of A, which is inverse of A square.
exchange it.
You can interchange this guy. So if you have the inverse of A, and I asked you to find the inverse of A square, multiply the inverse of A by itself. Okay? If determinant of A equal to 0, then the matrix has no inverse, non-invertible, or singular matrix. Is there some relation between the determinant of the inverse of A and the determinant of A? Is there a relation between these guys? One over. Can get it actually from this equation. Inverse of A times A equal identity. If you take the determinant for both sides, this guy is 1. And this guy is the product of determinants. So the determinant of the inverse is 1 over the determinant of A. Yes. Do you remember this when we said AB equal to 0? This does not imply necessarily that A equal to 0. احنا عندنا الاكزامبل ده في اول ليكتشر في الماتريسيز. But we say that AB equal to 0 implies A equal to 0 if there is some condition satisfied. Can you guess what is the condition? If B has an inverse. Because if B has an inverse, AB equal to 0. If B has an inverse, you can multiply from right by the inverse of B. Then you will get A, B, inverse of B equals 0, inverse of B. Then you will get A equal to 0. So this guy implies this guy if inverse of B exists. Okay? وعدينا على دي برضو لو تفتكروا. لو AC equal BC قلنا this does not imply necessarily that A equal B unless
لو سي ليها
if C is invertible. دي اللي بتعمل الكانسليشن اكشلي، كانك بتملتبلاي باي انفرس اوف سي كانك عملت الكانسليشن بتاع السكيلرز. طب هنا بس عشان نكمبليت الثيرم بيقول لك لو A كانت نون سنجلر اللي هي has an inverse يعني او invertible then A can be reduced to، تقدر تعمل reduction لل A till you reach الايدنتيتي، مش كده؟ مش جاوز جوردن بيعمل كده؟ يبقى ممكن توصل للايدنتيتي في الريدكشن. طب assume that we have a system AX equal B and you know that the matrix A is invertible. Can we get the solution directly of this system using the matrix inverse? If you have A n by n, X equal B, and you know that A is invertible, so can we get X? Left multiply by inverse of A, right? So we'll get actually inverse of AX equal inverse of AB, which is X equal, and actually you get this as your unique solution. So this is the case of unique solution. When A is invertible, you get only one solution, only one X, which is given by this formula. You get the inverse and multiply it with B, and then you'll get your vector X. عمل left multiply اسمك ايه؟ حاتم؟ حازم. حازم عمل left multiply with the inverse of A, both sides. يبقى inverse of A, AX equal inverse of AB. This guy is I times X, X. So you'll get X equal inverse of AB. This is your unique solution, huh? Unique. So the case for unique solution, you can get it by matrix inverse directly using this equation. So in some problems, actually, we can find that you are solving system when you have A and several B's. You solve X equal B for fixed A and for several B's, B1, B2, B3, and so on. So in these problems, one way to solve, instead of reduction, you can get the inverse of A using reduction, okay, and then multiply it with each B to get the solution in each case. في problems تبقى كده، بيبقى في مثلا زي سيركت، والسيركت دي السورس از تشينجينج، السورس ده بيبقى الفولتج هو البي بتاعي، والاي بتبقى الكوفيشنت ماتريكس containing مثلا الريزيستنسز اللي موجوده عندك في السيركت، والاكس بيبقى الكرنس اللي هتمشي في السيركت. انت بتبقى الفولتج بيتغير changing مع التايم، وانت بتبقى عايز تعرف كل مره الاكس الكرنت هيبقى ايه، والاي كونستنت ما بتتغيرش الاي. فممكن this is one way to solve. Get the inverse of A. This is a simple 2 by 2 matrix. فاكرين اللي بنجيبها ازاي على طول؟ اللي هي determinant هيبقى 2 يبقى 1 over determinant، وكنا بنinterchange دول وهتشينج الساين او the off diagonal. Then you have the inverse of A, multiply it with each B to get your answer. So this is X in this case, in this case, and this one. And as you see here, بص على الكيس دي كده معلش. If you have B equals 0, then actually we are solving AX equals 0. What happens when you solve AX equals 0 and A is invertible? تبقى ال X equals 0 على طول، ما لا تبقى A inverse times 0 هتبقى 0. اللي هي الكيس بتاعت الهوموجينيوس سيستم if you remember، بتاعت التريفيال سوليوشن only هو ده اليونيك بتاعها. معلش هما دول مكتوبين كارو عشان كده مكتوبه ترانسبوز دي، انت اكتبها فيكتور عادي. بس نلاحظ حاجه ما بين البيز هنا، this B is the negative of this B, therefore this X the negative of this x. And if you multiply this equation by negative, then you'll have a times negative x equal negative b. صح؟ كأنك كاتبها كده a times negative x equal negative b. So when you have the right hand side negative certain b's, then the solution would be the negative of this solution. Now لو البروبلم given اللي هي a و 3 b's مثلا مديهم لك وبقول لك solve, one way is to get the inverse وتمultiply لو هي invertible و square. لو مش invertible ولا square هعمل ايه؟ ايه الماجيك ميثود؟ الريدكشن. اكتب ال A augmented with ال B's. ادي ال A وادي ال B الاولانيه الثانيه الثالثه وات ايفر ال B's اللي عندك واعمل ريدكشن. بعد الريدكشن هتجيب السوليوشن للكيس دي ودي ودي. حتى لو ما وصلتش للريديوس رو اشلون فورم ممكن تحل بالايه بالاشلون فورم العاديه وتعمل باك سبستيوشن فور ايتش وان. دي اللي بتسولف اي حاجه. ها ماتريكس سكوير ولا لا، انفيرتبل سكوير وانفيرتبل ولا سكوير مش انفيرتبل، الريدكشن ده اللي شغال على طول. طب في عندي ثيرم بقى، هتلاقي الثيرم دي ما شاء الله يعني موجوده في الكتاب كده، في كل تشابتر ليها ستيتمنتس كده مكمله معانا يعني. هنقول حبه منهم النهارده. اسمها الانفيرتبل ماتريكس ثيرم. كل الستيتمنتس اللي جايه دي ايكويفالنت للفيرست وان اللي هي الاي سكوير ماتريكس والاي از انفيرتبل. This mean that شوف بقى بقيه الستيتمنتس وتكمبليت معايا. لو الماتريكس سكوير وانفيرتبل then A is row equivalent to you can reduce A to the identity. لازم نقولها كده يعني. طب A has how many pivots؟ لو هي n by n وانفيرتبل هتريديوس للI، يبقى معناها لقيت كل البيفوتس بتوعك ال n pivots صح؟ و x equals 0 will have unique solution اللي هو the trivial solution، و x equal b has يبقى ليها unique solution اللي هو given by ان x equal inverse of a times b. طب لو a invertible يبقى ال a transpose invertible. ايه رأيكم؟ determinant a equal determinant a transpose، فلو a invertible يبقى الديترمنت بتاعها مش زيرو اللي هو the same as determinant of a transpose، يبقى لازم هتبقى invertible. واحنا كمان كتبنا الفورمولا بتاعتها لو تفتكروا من شويه، احنا قلنا ال a transpose inverse هي ال inverse of a transpose، فانا معايا كمان شكلها عامل ازاي. فاهم؟ طب هل ده ليه علاقه بالديبندنس بين الكولمز بتاعت الايه؟ لو الماتريكس A انفيرتبل اقدر اقول حاجه على الاندبندنس او الديبندنس للكولمز؟
لو انفيرتبل فمعنى كده ان الديترمنت بتاعها مش بزيرو.
ايوه.
معنى ان هي الديترمنت مش بزيرو معنى كده ان في او يعني
خلينا نقولها بطريقه ثانيه. طب هو لو كان في اي ديبندنس جوه يبقى هتلاقي some row مثلا او column can be written as linear combination من الباقي، فهيبقى الديترمنت بزيرو فما تبقاش invertible. فهي لازم طالما هي invertible يبقى لازم الكولمز بتاعها كلها يبقى linearly independent. نفس الكلام applied على الروز زي ما اتفقنا. طب السبان بقى، فاكرين السبان؟ الكولمز اقدر اقول عليها هتسبان ايه المره دي؟ سبان السبيس بتاعها اللي هو الار ان كله، والروز كمان، والروز كمان. طيب اخر حاجه نبص على الاكزامبل ده سريعا كده. given هي الماتريكس دي وعايز ايفالويت الحاجات دي. طبعا في بعض الحاجات هتيجي بالبروبرتيز so you don't have to evaluate الحاجات دي in details، بعضها هتلاقيها بيجي بالبروبرتيز بسرعه قوي. determinant ايه الاول بكام؟ 6 مش كده عشان دي triangular، اتاكد بس انها triangular صح، يبقى product of diagonal entries. الانفرس اوف ايه انا هسيبك تعملها انت في البيت بقى، يا ريت تجرب الميثودز اللي قلنا عليها النهارده، الادجت وجاوس جوردن، عشان لو خليتك تجيب فري تحل باي واحده تشوف انهي الاسهل لك او اللي انت تحب تشتغل. هنا فيها سام زيروز فهتلاقي الايفورت برضو قليل شويه. طيب اسيوم ان احنا جبنا الانفرس، بص على الانفرس كده وقول لي ملاحظ ايه عليه بس. اي كومنت كده على الماتريكس والانفرس. the same shape انها lower دي upper، دي upper triangular فالانفرس برضو upper triangular. ايه كمان؟ الديترمينانت طبعا من الرول بتاعتنا هو 1 over the determinant. لا في حاجه اقوى كمان من بص الدياجونال انتريز هنا وهنا. بس انت هتعمل انت هتحط الايدنتيتي جنبك وبعدين هتخلي البيفوتس دي وانز، فهتروح قاسم الفيرست رو على 2 فال1 بتاعت الايدنتيتي تبقى هاف على طول، واخر واحد 3 ال1 اللي هنا تخليه 1 over 3 على طول. جربها بايدك بس عشان تشوف، فهتلاقي فيها البروبرتيز دي. فوانت بتيفالويت الانفرس اكشلي الحاجات اللي تعبت فيها هم ال 3 انتريز دول. انت عارف انها upper triangular ضيعش وقت، دول زيروز. عارف ان دول هم reciprocal of these guys ضيعش وقت برضو فيها 1 over على طول، يبقى بس اللي هتتعب فيه دول. طالما هم 3 دول ممكن تجيبها بقى بايه؟ بالادجت، ان انت بقى ايه مش هتكفر ده بقى، هتكفر ده عشان تكتب اللي هنا عشان فيه ترانسبوز ما تنساش. هتبان لك دي اما تكتبها بايدك بس. طيب جبنا الانفرس اوف ايه، نعرف نجيب بقيه الحاجات بقى. احنا قلنا اول اتنين كده خلاص. determinant of inverse of a يبقى 1 over 6. طب determinant of the inverse of 3a دي احنا قلنا ايه 1 over determinant of 3a مش كده؟ فاكر كان في property كده ايه تريكي وناس كتير بتغلط فيها، يا ريت ما نغلطش فيها. ال a هنا 3 by 3 صح؟ ف 3 بتبقى multiplied بكل الانتريز كماتريكس، بس لما تاخدها common في الديترمنت تاخدها from each row فبتطلع 3 power 3 determinant of A لو تفتكر البروبرتي دي. يبقى دي اللي هي 6. معلش اخر واحده المفروض A سكوير الانفرس اوف A سكوير الديترمنت بتاعها 1 over determinant of A square، و determinant of A square هي determinant A all square، يبقى دي 1 over 6 square. اوكي احنا قلنا ايه النهارده بقى؟ قلنا حاجه، قلنا جبنا الانفرس اوف ا ماتريكس using جاوس جوردن والاليمنتري ماتريكس والانفرس using الادجت ميثود وكرامرز رول والريليشن بين الاليمنتري والرو اوبريشنز، وعرفنا الليفت مالتيبليكيشن والسوليوشن بتاع x equal b using الانفرس، وشويه بروبرتيز بقى على الانفرس اوف ا ماتريكس. اي سؤال كده يا شباب؟ اي سؤال؟ شكرا جزيلا.